now we're going to get into the really practical aspects of this. Object detection seems like something that ought to be, it's an easy thing to say, but in point of fact, it's actually really hard to do. And it's particularly hard to do, if you're working with any sort of a constrained computing system. And it's the sort of thing where, hard-won experience matters a lot. Our first speaker is Nehemiah, and he is the product marketing manager for computer vision at MathWorks. And he has 10 years of experience with computer vision. Prior to that, he was working on a patient safety system in hospital rooms using computer vision. So, Avi, would you come on up? And I think this will be a really, really interesting talk with some hard-won practical knowledge.
Thanks, Phil. All right, so today I'm going to talk to you about, I'm hoping most of you got Jan LeCun's talk. I'm going to talk to you about the less sexy side of object detection. But these are things that you're going to need to remember if you actually want to create and deploy these things in a reliable fashion on an embedded system. I've got two objectives for this talk. One, for those of you who haven't created your own object detection systems before, I want to teach you the key steps that you'd have to follow if you wanted to create one of these systems yourself. And if you do decide to create a custom object detector, hopefully it doesn't have to be a 6-month research project. I'll also share some tips and tricks on how to create a great object detector. It's something I've learned taking my lumps unsuccessfully, trying to create many object detectors, and successfully creating a couple. I'll also talk about some design considerations for embedded devices, which could be the difference between an object detector running at 1 FPS on your cell phone to something that might actually work. So let's step back and motivate why would you create object detectors? Well, to put simply, they help us understand real-world scenes. We can feed in an image, and they detect the presence of stuff that's interesting to us, and they tell us where it is. So we can find faces to help just autofocus on our cell phones, and they make our cars safer by detecting pedestrians and stop signs. So object detection really is one of the most important things in embedded vision because it helps us find things that are interesting and important to us. So what is object detection? Really simply, it's the detection and localization of an object or a class of objects. And it's a little different from recognition, which is primarily what Jan talked about, which tells you what class an object is, or who a person is. It's a little different. Object detection really focuses on, is an object present in an image, and where is it? And another thing I wanted to point out is it's really hard to perform recognition without detection. If you don't have your object localized, it's really hard to perform recognition. So I wanted to take a second to give some credit. As part of this talk, I created a pedestrian detector just as the examples and to create data for this talk. And to do that, I used the in-rear person dataset, which is a great dataset for pedestrian detection. So the goal of an object detector is, given an image, you want to locate the object and non-object regions. So in this image here, I want to figure out which pixels belong to the pedestrians and which pixels do not. So those two bounding boxes there are my object regions. Now to do that, I first need to learn what a pedestrian looks like. So I need to use training data, which is a set of images that represents the object that I'm trying to find. So for pedestrians, it would just be pedestrians on streets and natural scenes. I also need my object detector to learn what a pedestrian is not. So I need to discriminate the pedestrian from an environment a pedestrian appears in, which are streets and other natural scenes. So I need a set of non-object regions to teach my object detector. And of course, creating an object detector requires thousands and thousands of images. You often use a more compact representation than just the pixels. And those are known as features, which Jan covered in quite some length in his talk. Now, one of the big stumbling blocks I found when people create object detectors is they say, hey, I want to create a face detector, and they go online and they look it up, and there's a lot of math, and it seems really complicated. And they either give up or they just try and use some pre-trained detector that's available to them. I was one of those people for my first 2 or 3 years doing computer vision. If I had an object detection problem, I did template matching. So you can imagine trying to create a face detector with template matching. The first system I created as part of my first job, it took 11 seconds per frame because I had a series of set templates that I was just correlating with my image, which wasn't particularly practical. So object detection at its very core is just simply, it's a data classification problem. It's a 2-class data classification problem. So for example, if you had this distribution of data and the object were the points in red and the blue was the environment, you want to classify whether any input point is a red point or a blue point. So you take the training data of features, you pass it through a machine learning algorithm, and you get that, which is a boundary or a classifier, which is the last stage that Jan talked about in his talk. And if you had an input point, you would decide whether it was the object or the red points or the environment or the blue points just by looking at which side of that decision boundary it fell on. So bringing that back to the pedestrian detector that I was talking about, I would take my image features, pass it through a classifier, and that would just simply give me a label, whether it's a person or a non-person, and some sort of response. It would be a confidence whether that was a person or a not person. Now, there are already five steps if you did want to create an object detector. And I'm going to talk briefly about each one of them. Now, the first step is probably the most important step, and it's probably going to take the most time because a lot of the work in here is often manual. And that is collecting training data. If you want to create a good object detector, you want to be able to tell your object detector exactly what the object looks like, and you have to capture all of the variation that you're going to see when you do deploy an object detector. So you need samples of the object at different scales, orientations, environmental conditions. So that, as you can see, I have images of a face. Now that handsome gentleman is Dima Lyson, who's one of our senior developers of the computer vision toolbox at the MathWorks. And you also need negative data. So you want negative data that represents the environment the object usually appears in. So for my pedestrian detector, that would be streets and other natural scenes where pedestrians are normally walking around. Now, there are 3 things that you want to keep into account when you are collecting your training data. If you don't have enough positive samples that represent the object, you're going to end up with a detector that is insufficiently able to learn what the object looks like. And that's going to lead to a pretty low true detection rate. If you don't have enough variation in your training set, so you might have a large training set, but that it just has some very specific images. So for example, if I created a face detector using just those images of this one person there, and I ran it through an image, I would have a detector that could detect that one person's face, but not localized to all the other objects it needs to detect. And the third thing, and this is really key, is too few negative samples would lead to a detector that has a lot of false positives, where you would think part of the environment is the object that you're trying to detect. And it's also key to remember that these negative samples really need to represent the environment the object appears in. So for a pedestrian detector, you wouldn't be very well served if you had a lot of data of negative scenes which are indoors, because pedestrians by definition normally appear outdoors. Now the next step is another stumbling block, and this is where not most, but a lot of people stop trying to create their own object detector because there's this manual time-consuming step where you have to take all of your training data, you have to crop out the object of interest that you're looking for, and you have to label, normalize, and resize them so that you have features of the same size to feed into your final classification or learning algorithm. And here it's really, really important that you have the right tools to cluster your data and label them so that this part of the workflow isn't a roadblock. Now the next step is feature selection. Now Jan talked a lot about automatic feature selection. I'm going to talk about the old school classic mainstream features that we still use in object detection. But I'm going to try and give you an intuition as to why you would perform feature extraction. Well, to put simply, feature extraction it's a slightly different representation of the image. So if you look at the representation of the image with the image pixels there, that's really dependent on having the full bicycle in the view. It's really dependent on the illumination in that scene. A feature extraction step helps remove some of that variation. So if you look at the hog feature right next to the image pixels, you can still discern the structure of the bicycle, but that's now a representation that's invariant to changes in illumination. If you look at the bag of words, or the parts of the bicycle on the left, you can now represent the bicycle as the sum of its parts. So that makes it invariant to occlusion. If part of the bicycle is hidden, you could still detect it by detecting some parts of that bicycle. And of course, it's exciting times when there's new feature extraction methods, automatic feature extraction methods, like the ones Jan talked about on convolutional networks. Now, the next step is to figure out what classifier. So you need, the final thing you need to do is you need to feed your features into a classifier, and that tells you a decision whether it's an object or a non-object. So you need to try to create an optimal object detector. You need to try a few different classifiers to figure out what works best with your feature type and what works best for your data. Now, there's a few steps to evaluating the best classifier feature combination. Now, the first step is to randomly take a small subset of your training data, which I know it seems like it contradicts what I said, that you need a lot of training data. But the reason you want to do this is training a classifier with a lot of data for an object detector, it takes a lot of time. So it could take hours, it could take days. And what I'm sure you'd like to do is try a few different classifiers and figure out what works best for your data before investing the time in really training your final classifier. So you want a method to randomly sample your training set so that you can try a few different classifiers. And the next thing, obviously, is to train several different types of classifiers so you can figure out what works best for your feature type. And then you compare the performance of the different classifiers, which I'll address in a second. Now I know I just talked about classifiers. So let's go over some of the important classification methods or popular classification methods that you see nowadays. So the first method is supervised classification or discriminative classification. And an example would be a support vector machine that's used in the standard pedestrian detectors that are available, or a neural net. Now, a supervised classification method uses a labeled set of data. So as I mentioned in the label and normalize step, you take the images, you crop it out to say what the object is, and you give it a label. So you say it's a person, or a car, or a stop sign. And this supervised classification is fantastic, especially when you have a low variation in orientation and appearance, and you're able to create that label training set. Now, unsupervised classification is more similar to clustering, and this can often be used as a precursor to supervised classification. But if you have a lot of data and you don't know how many classes you have and you wanted to cluster them, an unsupervised method would work particularly well. And the last method are ensemble methods. Now, the most popular ensemble method is AdaBoost, which was used to train the Viola-Jones face detector, which is one of the more popular object detectors, and it's one of the most robust. And it was probably the first detector really to gain attention because it worked fast and it worked well for face detection. And the concept behind an ensemble method is no one classifier is good enough to represent the entire variation you have. So it takes an ensemble of classifiers and cascades them and uses that for the classification. So it's more robust than, say, just one supervised classification method. But the drawback is it takes an exceptionally long time to train, and it's pretty difficult to implement the training process. So now let me give you an example of what a classifier does. And this hopefully will give you some insight into the things you need to consider when you're moving to an embedded device. So if I had this simulated data here and I wanted to create a classifier, to separate this data. If I use the support vector machine classifier, it would create a boundary that looked like that to separate the blue and the red points. And to create that boundary, it uses what are called support vectors, which are those points with the black circles around them, which are right by the decision boundary. So if I did have to deploy a support vector machine on an embedded system, I would have to store all of those support vectors because I would need that to reconstruct that decision boundary every time I wanted to classify a point. Now the next thing to do is once you've trained up a few different classifiers, you want to analyze your classifier performance to see how it did before you move on to your next stage. Well, the first way to do it, obviously, is just simply the eye test. Run it through some images and see how it does. So here I have two examples, one of a correctly classified pedestrian and one of an incorrectly classified person. Now, the good thing about the eye test is it can tell you where you're making mistakes. So I might run my classifier through a few different images, and I find that I'm mistaking skyscrapers for pedestrians. Now, what that tells me is I don't have enough skyscrapers in my training set, so my classifier is having a hard time discriminating skyscrapers from pedestrians. Now, the eye test isn't the only thing that you need to do to evaluate the classifier, because it's not an objective metric. And one objective way of evaluating your classifier to figure out what works best is something called an ROC curve, or a receiver operating curve. And a receiver operating curve has its origin in communication systems, and it's a really good way to objectively figure out which classifier is best. Now, on your x-axis there, you have the probability of false positives. So those are the number of negative samples of the environment that was incorrectly classified as the object, and the probability of true positives, which is on your y-axis. Now, an ideal curve is closer towards the top and towards the left, where you have a higher degree of true positives and a lower degree of false positives. And another way if you wanted one single number to compare two classifiers, the area under the curve, the higher the area under the curve, the better your classifier is. Now, the next step is to actually construct the detector. So let's take a second and figure out where we're at in the workflow. So we have a method that takes a block of an image, it converts it to some sort of feature type that you've selected. You now have a classifier that can take in that feature type and give you a label, whether it's a person or a non-person. But an object detector's job is not to label blocks of an image, it's to tell you where the object is. Now, to get that localization, what you do is you slide your classifier across the image, and then you resize the image and you do this at a few different scales. Now, what this does is it gives you the scale invariance, and it also allows you to not have to train different classifiers for different scales, because it's not only is it hard to collect that training data, it's pretty hard to label the data, and it's much more cumbersome. So an easier, more efficient method is to simply resize the image and just use a classifier at one scale. So if you did run your classifier across the entire image, or this entire image, you'd end up with a series of boxes where it said the label was a person and it had a response above a certain threshold. And the next thing to do would be to figure out what your strongest bounding box is. And there's a variety of methods you can do it. You can simply average out all of the overlapping bounding boxes, or you can use a more involved techniques called non-maximal suppression, which resolves the detection scores and picks the strongest bounding box. Now, this is another place where you can really optimize your localization by adding different metrics that are specific to your problem to figure out how to pick the strongest bounding box. Now, the last step, obviously, is to optimize for embedded implementation. So often the goal of creating these detectors is so that we can find faces using our cell phones, or find pedestrians in our cars, But we need to move these detectors onto embedded devices. And there's three things you need to consider. And this is something that you probably want to keep in mind while you're performing your feature selection, and especially when you're selecting your classifier. One, what is the memory footprint of your classifier model? So for a support vector machine, as I mentioned, you'd have to store all of the support vectors. So the memory footprint is dependent not only on the number of support vectors you have, but the dimensionality of the features that you have. If you used a nearest neighbor classifier, you might, for certain kinds of classifiers like that, you might have to store all of your training data, which would have a huge memory footprint. You might use an unsupervised method to cluster up your training data. So then you would just store the cluster centers, which is less memory intensive. The next thing you need to consider is processing time. And that is, what is the classification time for each window step? Because when you have a sliding window, not only do you need to consider at what granularity are you sliding the window across that image, you also need to be aware of what the classification time for each window step is. Also, do you have some way to optimize that? So support vector machine is simply a series of dot products and additions. Now that is something that can be very easily optimized in hardware, so it lends itself really well to being implemented in hardware. And there's other methods where you can cascade several different classifiers to quickly reject negatives, so you don't have to go through the entire classification process. The other thing that you do want to be aware of is fixed point issues. Now the classification and the feature extraction, very often when you're prototyping these systems, you do it in floating point. But if you're going onto an ARM processor or a processor like that, implementing this in fixed point is probably going to give you a real speed up. So you do want to be aware of the sensitivity of not just your classifier, but your feature extractor to being converted to fixed point. And that could make a big difference. So you might end up choosing a simpler feature or a binary feature that works better when it's converted to fixed point than something that works really only well in floating point. And the last thing is consider dimensionality reduction. So when I created my pedestrian detector, I used a hog feature extractor because I had an optimized implementation of it. And that had a dimensionality of 7,500. So each image patch that I passed through it, what I got out was a feature vector of length 7,500. And I used something called principal component analysis, or PCA, to reduce that dimensionality from 7,500 to 300. And what that did is when I trained my SVM classifier, I had less support vectors, one, and two, since my feature was of a lower dimensionality, the number of operations required for each step of that sliding window was substantially less. And that gave me about a 99% speed up with maybe a 2 or 3% loss in accuracy. And these are the trade-offs that you're going to want to consider when you're trying to optimize your detectors for embedded implementation. Now, the last thing to remember is if you want to create a great detector, there's going to be a little iteration, one or two iterations between trying to figure out what the best feature is and what the best feature and classifier combination is. Now, when I created my pedestrian detector, I used a few MathWorks tools. So I used MATLAB and the computer vision system toolbox to collect the training data. There's an app that helped me label my training data really quickly, and also to perform the feature selection. And then I used the statistics toolbox, which gave me, I think, 8 or 9 different classifiers that I tried before I figured out linear SVM probably worked best for me. And something else that was really cool is I used a parallel computing toolbox that let me train my classifiers on a network or on the cloud. So something that would take me 4 hours to train on my desktop, I could offload that processing. It would be done in a few minutes, and I'd get my results back, and I'd try a different classifier really quickly. And then to construct the detector and to optimize it for embedded implementation, I took it out of MATLAB using some of our code generation products. So here are some key takeaways. If you know the right steps, it is not difficult to create your own object detector. Smart feature and classifier selection is really going to help you create that great object detector. Never ever solely rely on the eye test for evaluation. It is never sufficient. Always try to use a method to objectively test your classifiers. And the most importantly, insufficient training data is really going to hold you back. And here are a few resources if you do want to learn more about computer vision, machine learning, which is what you'd use to create a great object detector.